This is a little demo prop that I made. It uses a hard drive motor, which some of them have 4 wires, some of them 3. The 4th wire is the neutral point, which is where they take the other end of all 3 windings and tie them together. And I put some LEDs on here to show whenever the coils A, B, and C are either being energized forward or reverse, since they take turns like that. And it happens pretty quick, so once the motor gets going it just looks like they're all on, but if you looked at it through a slow-mo camera you'd be able to watch the rotor position and the LEDs. It's actually pretty difficult to do this sort of motor control development with a power supply that limits at 3 amps. 3 amps is great for most circuits, but when the motor turns on, the power supply sees such a huge transient that it overreacts and drops the voltage down. So once the motor is starting, it produces a voltage that opposes the supply voltage, and you'll see the current actually gets less and less as the motor gets faster, which sounds weird, but watch. So right now we're about 0.25 amps. I'm going to take it up. Okay, and my timing is probably a little off. Okay. So now, right now up on the oscilloscope, we are looking at a timing pulse, which happens once per electrical revolution, which is actually once every 6 steps. And then on the top we're looking at a very messy PWM signal that's coming from phase A. Let's jump over and see what the analog to digital converter is doing. Here's some more timing. The blue, there's a little pulse each time we commutate, and then after that the ADC runs several cycles as it's searching for it's trying to measure the voltage, and so it's watching for a 0 crossing. So the problem I'm having is you have to get the motor to build up enough speed that it starts acting like a generator and sending voltage back, which the Arduino can then sense the exact speed of the motor and figure out where the rotor is, because it wants to turn on the coil which will produce the most torque, and that will be the coil that is just ahead of the current position of the rotor. But right now it's starting blind. It's just timing it, but then it can't find the back EMF voltage. The software is broken into 2 sections. Starting the motor, and once we build up some speed, then we have a feedback loop, and then we commutate based on the rotor position. So first, when we want to start the motor, we just commutate and then wait a bit of time and then commutate again. Commutate just means advance to the next coil. And then each time we'll decrease T so that it commutates a little faster, and you want to get that ramp up of speed going. Then, once the speed is high enough, then we switch to a new routine. Then we commutate. We'll calculate how much time since the last commutation, so we're keeping track of the duration of, or the time between commutations. And then there's a period of time where if you're energizing the black and the red, then the yellow is unused. If you're energizing, okay, so there's always one unused coil, and you can sense the voltage on that one. You can't sense the voltage on the ones that are being driven, because they'll either be they'll be the positive supply rail and ground. So you sense the unused wire, and then you watch for a zero crossing, either rising or falling edge depending on the commutation sequence. And then once you find the zero crossing, you want to schedule the next commutation for t over 2. And that's because the zero crossing is a marker of the rotor position, but because the back EMF is delayed a little bit, you don't want to commutate right at the zero crossing. You get the most torque if you commutate half of a cycle. And so here's the commutation steps. And if you want to generate this list, you just start with AA, B, C, C. And then on this side, we're going to do A to B will be the first one, and then C, C, A, and then back to B. Well, that's a quick overview of what it takes to get a brushless motor to spin without in a sensorless configuration. So it gives you some appreciation for that.